When we use polar coordinates to solve a double integral, we usually substitute dA with r dr d theta. Where does this extra r come from? When I was learning about this, it made sense for dr d theta to be there as we are varying those variables, but I was always skeptical about this extra r. In this video, I will try to make you understand this concept. To start off, I will be assuming you know some of the other Calc 3 concepts such as partial derivatives, surface area, vector equations and functions, functions in 3D, and some basic double integrals. Let's start. When we're solving a double integral, we usually replace dA with dx dy. But why are we able to do that? What is dA really? Let's just say we are integrating over a semicircle of radius 2 in the xy plane. dA is the area of this infinitesimally small piece of the region. Likewise, the infinitesimally small length and width of this piece are dx and dy. Using simple geometry, we get dA equals dx dy. And there we have it. But this is only useful when the region is a simple one. That is, when the bounds of x and y can easily and fully describe the region, just like in this case. Then we can just plug in the bounds into our integral and solve it. But what if that's not the case? What if the region is much simpler to describe as a parameterization? Let us take the same region D and pretend that we only know the parameterization R of u and v of it. Zooming into this infinitesimally small parallelogram, just as with the Cartesian version, we get dA. We're looking for the length and width of it. Well, what is it? Just by the definition of a parameterization, we get these as the answers. And now, using some simple algebra and the definition of partial derivatives, we can simplify these to Ru du and Rv dv. And now it is simple. We just apply the formula for calculating a surface area of anything. And there we go. We've got ourselves a general formula for dA for any parameterized region. Before we move ahead, let us test this. We know from earlier that if we have a simple region, we should get dA as dx dy. So do we? A simple region just has the parameterization r of x and y equals x comma y. Let's calculate the partial derivatives. The cross product. Take the magnitude. And finally, plug it back into our formula. Nice! We indeed get dx dy. But how does this all relate to polar coordinates, you may ask? To review polar coordinates, we basically have a change of coordinates from x comma y to r comma theta, with x equaling r cosine theta and y equaling r sine theta. But we can also think of polar coordinates as a parameterization. And once we have that, our formula does the rest. Just like before, let's calculate PR and P theta, the partial derivatives. Calculate the cross product. Take the magnitude. And finally, plug it back into our formula. And there we have it. dA equal to r dr d theta.